doing work and understanding the properties through models are important. And an academic from UK, and we done this chapter. And Ahmad Zaini was my PhD scholar. He's now full-time employed. Myself and Chawla is Professor Harminder Chawla. He was in mechanical engineering faculty in IIT Delhi. Okay, so I had interacted with him, and we had. So this is the book chapter. So it not just gives our own results, but it covers the publications in the thing. Modeling, examination of mechanical properties of fly ash, polypropylene, particulate composites. That is the work which Dr. Ahmad Zaini had done as my research scholar, but then we have to model it, match it with different models to see which model or this fly ash, polypropylene, particulate composites fit more. So this is photography of polypropylene powder used in this research. So he put it just, they are normal particles. I asked him to put a scale bar, but he said no, his eyes have scale bar. So I said, all right. But this is how it look like. So the fly ash which Dr. Kaur showed you yesterday, if you put it on a just pour it on a paper on the table, so it looks. Now this is a bit whitish fly ash, but no, this is not fly ash. This is polypropylene. That's why it shows white. But if you put fly ash, they also look the same. But it's still always better to put a scale bar there. But it says it's magnified 1.5 times. So we'll go to the third para. Our recent results on mechanical properties of fly ash propylene composites obtained on our laboratories have been examined in the light of available models. These are introduction I don't need to give. This is a polypropylene chemical structure. It's worthwhile putting it in. All right, so you have CH2, CH3, and you have oxygen and carbon. N is the degree of polymerization. This is what N is. You put these things together, and this is the monomer, and put number of things together. This becomes the polymer. It has good rigidity and high thermal resistance, but with limited impact resistance at low temperature. So in another work, future work will show, by putting fly ash, we could actually improve the impact resistance. And this is, I often check with people from industry and things like that. You are familiar with CPET? You know CPET India? Yeah, Chennai is the head office there. Yes, I've been there several times. And but when CPET Director General Dr. Sanjay Naik came to our university with his team, and then he saw that, as I will show in a future slide, not future presentation, that using fly ash and polypropylene in fact had improved the impact fracture strength by about 50%. He was very surprised. He said, Dr. Bandyopadhyay, we must take up this thing, because because polypropylene is very prone to brittle impact fracture. And he said, if fly ash itself is brittle, say a mechanic putting fly ash, then I said, yes, we can. And that is what all this bonding and the things like that. And that is normal fly ash. You don't have to put any chemicals or anything. All right? What happened? What is the difference between this normal tensile testing and impact testing? So all of a sudden, there is no time. Not even half a second, 1 second, okay? So if there is the time, what happens? it does not allow the plastic to undergo deformation. It does not, like if you're doing a tensile test, some of the slides which show that you actually fabrication in between, but when you are doing an impact test, no such thing there. So there has to be, if you have to improve the impact test, there has to be something which is inbuilt there, no time. Okay? So that's why he was very surprised, and he has been the Director General of CPET so far about 8 or 9 years, and he said, how come fly ash can improve the impact strength of polypropylene? I said, that's what it does. And he brought his scientists, and one of the scientists worked on the fly ash thing. We'll get back to that later. But polypropylene otherwise is quite attractive because it has much better properties, stronger than polyethylene. For unoriented homopolymer of polypropylene, these properties are controlled by the morphology, which is determined by additives added into the polymer, process conditions, and the exact polypropylene structure. Now again, going back to what is the importance of fly ash. Fly ash is very cheap. And if you can go to the coal manufacturing plant, and if you can say, can you bring our trucks and take you to fly ash? You say, yes, take your fly ash and come and sit down and have tea and coffee with us and come every day and things like that. Now, to them, fly ash, they don't use it. But to other people, polymer industries, refractories or putting second phase in is very important, but they are quite expensive. So this is what is the advantage of fly ash. Factors influencing end-use applications of polypropylene. You have polymer structure, process additives, and this is polymer structure, process additives. Then morphology, physical morphology of the polymer, physical properties of the polymer. Then end-use properties, rigidity, high thermal resistance, limited impact resistance at low temperature. So this is a limitation. Then it has orientation, and you can put fillers. All these things you can do. And these are the factors which influence the end-use applications. I'll just sit down for 5-10 minutes, okay? This shoe is a new pair of shoes, and it's not matching with me. He said, you have not given any coating on me. Why should I? So he said, I'm polypropylene in your fly ash. You have to give a coating. Okay. But I said, no, I'll go my way, and you have to come down to me. I said, okay. But sometimes you have to be friendly to each other. All right. 3 aspects of polypropylene structure determine the physical properties of fly ash. Stereospecificity, that means tacticity. Molecular weight and molecular weight distribution, as discussed in the next slide. But this is also taken from this handbook published in Munich. Where is Munich? Which country? Germany. Very good country. Have I told you once I had been to University of Kaiserslautern and I picked a wrong train from the airport. I took a flight, went to the airport, and then they have underground, they have trains. And I said, I have to go to Kaiserslautern. Which train? And the guy said, this is the train. So I get into the train, and after 1 hour I asked another passenger, I have to go to University of Kaiserslautern. How long will it take to go to Kaiserslautern? He said, are you mad? I said, why? This train is coming to Kaiserslautern and it's going to other states and other countries in Europe. So you will not reach Kaiserslautern, you will go to other countries, Spain and other places. And then there was one, I said, so what to do? Then there is one German friend, he said, hang on, see on the other platform, this train is standing? On the other, I said, yes. He said, where is your suitcase? I said, there is. He said, come with me, get down from this train. And I get down, he said, you cannot carry the suitcase, I'll carry it. He carried the suitcase, crossed the other line. He said, just get into the platform and run to the other train. I said, don't ask questions, that train is going to Kaiserslautern. So that was a correlation and friendship I had with that unknown German gentleman. I'll never forget that. And then I went into the train, and within 5 minutes the train left, and when I showed my ticket to the inspector, he looked at me, he wanted to say that, how come your train is from the other airport station to Kaiserslautern? How have you come here? I said, I was told and I took a wrong train. But, oh my God, we would have landed up in other countries. Okay, but that is wonderful. That is wonderful. That's why I love God. Whenever something goes wrong, always it gives you something positive. All right? Things at times go wrong. Follow it, but then it leads you into new information, new world, new life. Including fly ash composites. Okay. So the molecular weight distribution, what it means to people who are not familiar with polymers. Molecular weight means, you know that you have the monomer and N is the number, how many monomers are there. But all molecules do not have the same number of monomers. Some may have 1,000 monomers, another molecule may have 5,000 monomers, another molecule may have 10,000 monomers. That's how the thing happens. Even there are some molecules which may have 100,000 monomers. Okay? So that's how it actually controls the properties. So when you buy the commercial things, their table or their information table gives you all this information. But please note that thermoplastics have, which you get that the molecular weight distribution is there, and there are some formulas for that. Now, tacticity is isotactic, symbiotic, and atactic. What? Isotactic means that you have all the carbons or something like that on one side. Symbiotic is you have one on this side and symmetrical, but it goes on like that. And atactic means you don't know which one goes where. But that is how the stereochemical composition of polypropylene and most polymers. And how is it obtained? Isotactic polypropylene is obtained when methyl groups are always in the same configuration with respect to the polymer backbone. Symbiotic is when the methyl group has an alternative configuration, which means this can give you more uniform properties because you have methyl, all right? Atactic polypropylene is results when the methyl groups do not have any consistent placements. The tacticity determines the order of crystallinity of polypropylene. So if you have too many molecular weight distribution, then it can affect the crystallinity. Okay? And crystallinity gives you the regularity of the structure. And amongst many methods for determining the tacticity of polypropylene, X-ray diffraction is the most important technique used. The XRD pattern or the peaks of polypropylene indicates that isotactic and symbiotic polypropylene are semi-crystalline material, whereas atactic polypropylene is a non-crystalline or amorphous material due to a very broad scattering in the XRD. So this is what, when you are buying polypropylene, or engineers and anyone, doctors, engineers, scientists, whatever it is, school teachers, when you are buying things or polymer chemists, make sure you know what kind of polymer. So go through the table and see what kind of polypropylene it is, because that will give you the difference from crystallinity to amorphous. Normally polypropylene is considered as crystalline polymer, but it can also become amorphous polymer. Amorphous has advantages, crystalline have advantages. So if you have the polypropylene, this is isotactic, that means you have the X-ray diffraction. These are the sharp pricks, And these sharp peaks relate to crystallinity. All right. Even ceramics. In ceramics, you get sharp peaks because ceramics. Sometimes people say they're brittle, but ceramics, the peaks are sharp, means they're crystalline thing. All right. Syndiotic. Here you have some peaks are sharp, but overall the number of this sharpness has come down. This syndiotic. And atactic is like, if you look at epoxy, you will see something like that. All right, except for the fact that epoxy is at higher glass transition temperature or is depends on, whereas polypropylene has another range of glass transition temperature. So this is isotactic, this is syndiotic, this is atactic. Molecular weight is another major factor that affects the crystallinity or toxicity of the polypropylene. Low molecular weight polypropylene has high crystallinity due to rapid rearrangement. If you have low molecular weight, they can arrange very quickly. But if you have limited broad distribution, that will not allow much of thing. But anyway, also low molecular weight means that there are more chain ends in the structure, which results in a fewer number of chains completely integrated. Is that all right? Because, for example, if you have, how many chairs are there in the class? About 100? Why are there 100 chairs? Because each one has separate things. But instead of the chairs, so there are number is let's say 100. But instead of the chairs, if there are a bench without any separation, so there will be one bench, two benches, and there are rows like 10. So 10 times 2, 20 benches. So there will be 20 ends of molecules. Each bench has 2 ends. But here you have chairs, each chair has 2 ends, so you have 10 ends. You have 10 ends there, or maybe 12. So it's the polymer, and it's the ends which matters, because the ends will react with the other things. Okay? Low molecular weight polyethylene thereby means that there are more chain ends. So low molecular weight polyethylene is like these chairs, but instead of the chairs, if you had a bench, so you had only 2 ends, whereas you have 10 or 12 ends. So that is resulting in decrease, and low molecular polyethylene actually states that the crystallinity resulting in decreasing of impact tensile and elongation. So whereas they have more things, because every time you have a chain end, what does it give? So if there are benches, and I can go through like that, okay, so every time there is a chain end, and a chain end is like a break in the chains, okay, and there is a stress concentration there, so there is something like that. And if the stress concentration is high, the tensile strength will go down. But if you have less chain ends, then over that long chain, long bench, there is no stress concentration. But here, if you have like that, then there is stress concentration at the end of each chair, okay, because there is a void, and it cannot take the load. Molecular weight is, oh, I thought someone is pushing me. I'm pushing, all right. Yeah, I think we have talked too much. Let's sing a song. Should I sing one of my songs or your songs? Idhar dekha, udhar dekha, dekha andar aur bahar. I have said that, so we'll leave it there. I also wrote a song on Saurabh Ganguly. You know Saurabh Ganguly? But that was in Bengali when I originally come from half Benares and half Kolkata. And after many years ago, Pankaj Rai, there was no test cricketer from West Bengal. And then when Saurabh Ganguly came to play, and he was playing in England, I said, hang on, Saurabh Ganguly looks like someone from Kolkata, my home city, half home city. They said yes. And then I wrote a song on him, and then it came out as a CD. And then I went to Saurabh Ganguly's home. They said in Bayala, and I went and asked them, and they said yes. They took me there, and I gave the CD, and then his father, Dr. Chandi Ganguly, he loved that song. And then he said, next time you are in Kolkata, please, you have to come into my house, you have to eat. And then I went there and their entire family was there. So I'll just sing a couple of lines of that song. Bengali, Hindi, Malayalam, Tamil, they are all similar. All right? আমাদের সৌরভ গাঙ্গুলি ব্যাট করো বল করো ভাই তুমি সব কিছু ভুলি আমাদের সৌরভ গাঙ্গুলি that means to me he was then playing against England so हमारे सौरभ गांगुली तुम बैट करो और बॉल करो और सब कुछ भूल जाओ मारो छक्का मारो चार छय मारो और चार मारो मारो छक्का मारो चार बाउंड्री लाइनটা দাও করি পার make sure your ball always goes over the boundary एक रन दुई रन साथ नियो तुली उसके साथ एक रन और दो रन भी ले लो আমাদের সৌরভ গাঙ্গুলি হোক না শারজা হোক না ওয়ার্ল্ড কাপ আম্পায়ারের আঙুল যেন না হয় গোয়াপ দ্যাট মিনস whether it is Sharjah or World Cup make sure when you are batting umpire's finger does not go up that means don't get out হোক না শারজা হোক না ওয়ার্ল্ড কাপ আম্পায়ারের আঙুল যেন না হয় গোয়াপ সেই সাথে নিও কিছু উইকেট গুলি সেই সাথে নিও কিছু উইকেट गुली उसके साथ विकेट भी ले लो तो बॉलर भी है ना तो ऐसे ही चला उनके पिताजी की इतना अच्छा लगा और बाद में जब when Greg Chappell came and he sacked Saurav Ganguly from the captaincy and then I was a professor at JNU then I said how did Greg Chappell come but then that was a different thing okay I said Greg Chappell was invited as a coach and then Saurav Ganguly's father said, Dr. Bandyopadhyay, you know how we spend this time? He said, every day we listen to that song on Saurav Ganguly, every day 10 to 12 times. We run the CD the whole day. Then I had tears came through my eyes. I said, are you really serious? He said, yes, we love that song. So that song was on website also, MBC Australia. So that was good. I love Indians when they play cricket because cricket is a gentleman's game and Indian cricketers are very gentlemen. All right? Thank you. So I'll finish that song another time. But it's good to have a break, isn't it? In between. If any of you can sing a song, a line or two, that will be good. Any language. You can sing a song, Dr. Abdul? Sing a couple of lines and tell us which language it is. Arabic. Oh, good. Please sing a couple of lines. Okay, and that's good that we love songs and it's a love song. Okay. Thank you. Thank you. To me, it sounds very much like Urdu and Hindi. Yes. But yes, thank you very much. We'll have to add these songs in our list. All right? So one to see, love exists anywhere and everywhere in the world. And when you are doing composites, you have to generate love between the particle and the fibers. Okay? And the more the love becomes, the better is the composites, the better is the life. Thank you. Now the crystallinity of, thank you very much. And thank you all for your time. It gives a change, isn't it? And it gives a relaxation. We don't have stress concentration, but stress relaxation. It is observed that the crystallinity of polypropylene is increased with increase in molecular weight due to lower molecular weight parts. Okay, so let's go to some models for predicting properties of composites, because we have talked about polymer composites, and let's take a look at some of the models. Models predicting the properties of particulate composites are important, because before people make the composites, you have to work out in theory, if you are going to make composites, how much improvement you will get. In the research field, that's all right. You have time and you can make 3 or 4, but in the industry, they don't have time to waste, okay? So they will ask, hang on, if you are going to get this reinforcement, how can you, if you put it in a matrix and what it, so you have to have models. That means models are equations. Like I mentioned earlier, that when you do the blasting in mines, so you do the blasting, the engineer actually is doing generating the model and the time and everything. So if things change there, what the engineer has to do, the engineer has to put all those information in the computer program. The computer program will tell you it will take this much energy to blast and this much and things like that. So those things you have to know before you do the blasting. Can you see that? Once you do the blasting, you cannot change it. So that's why models are important. Models are important, all right? So all of you, whether chemists, doctors, material scientists or engineers, any engineers, you have to be familiar with some of these models. So you can at least compare these different things by different models. The models predicting the properties of particular field composites, they can actually extrapolate the conclusions, and they can reduce the number of avoidable experiments required to achieve the composites with their performance. Okay. When all parameters predicted from the application of a particular model are optimized, but still the properties are not expected, then they can be improved by introduction of other compounds. And this added compound can act as a bridge to connect matrix and the filler. Now when we talk about bridge between matrix and the filler, you remember those scanning electron microscope? So that shows a real, and that is where a real picture is important. That's why if your boss you're there, say, how do you know it will happen? You can show that as a micrograph. You can copy that and you can keep it in your iPhone or whatever it is. You take it out and that's 100% proof, okay? It forms a bridge. Now it is usually necessary to choose an appropriate modifier for improving mechanical properties of fly ash filled polymer composites. So that's what we have seen that. Now factors determining the properties of particulate composites is what is the components, what are their compositions, structures and interactions. So these are lists of the published literature. Now the load is carried either by the matrix or filler depending on the relative load bearing capacity. So what means if the matrix is the matrix is holding the particles. When you're applying the load, naturally the load is going to the matrix. Now if the matrix is strong, it will carry the load, and then the this reinforcement can do some. But if the matrix cannot take the load, what it will do, it will quickly transfer the load to the reinforcement, whether particles or other things, okay, before breaking. So, and even if it breaks a crack, if the reinforcement is there, the crack will go, and if this is the reinforcement, the crack is going, the reinforcement will stop the crack. Then for the crack to propagate, it has to either crack this particle or the fiber, or it has to go up like that and do other things. But that's the secondary thing, all right? When the matrix is weak, the filler will carry the greater part of the load and it will reinforce the polymer. But when the matrix is stiff, like if you are having steel, and then you are putting There's a lot of metal matrix composites also. Are you familiar with metal matrix composites? Anyone has worked in metal matrix composites? No, you can put in aluminium, you can put fly ash, or you can put in silica, and yes, all the aluminium can take the load, okay, and deformation. Steel can do the same thing, all right? So that is an example, accomplished mechanism. When the matrix is stiff, that means stiff and strong. Aluminium, magnesium. Magnesium is not as stiff, but still, a lot of these satellite structures in India, they use magnesium-based alloys because magnesium has low density, 1.7 grams of cesium compared to aluminium, which has 2. So if you're using magnesium, the weight of the satellite becomes about 2/3 of the other one, okay? And that burns less fuel. So when the matrix is stiff, the matrix will carry the load and the stress will develop around the filler. It increases the possibility of deponding and causing deformation if matrix is stiff. So that is one disadvantage, all right? And the volume fraction, here it shows tensile strength of calcium carbonate filled polyolefin. Polyolefin here is LDP, low density polyethylene, and bottom graph is polypropylene. In the case of this polyethylene, when you put the volumetric, it keeps on going up. The relative yield strength goes up by about 100% from 1 to 2. But in the case of polypropylene, it comes down by about close to 40 or 50, 45%. So you have to know that, and knowing on the basis of that, you then decide whether you are going to use one particular material or another particular material. The filler plays an equally significant role to the matrix in determining the composite properties, and almost every aspect of the inherent properties of the filler strongly affects the properties of particulate filled composites. So now the inherent properties like chemical composition, morphology, particle size and particle distribution, they are discussed in the next slide. Chemical composition. It influences the performance of the composite. High lime fly ash with high calcium content. So what category of fly ash is that? Thank you. C. And a better contact with the polymer. So if you're using a high lime fly ash or category C fly ash, it has a better contact with the polymer. And then the purity of the filler can influence the performance of the polymer both directly and indirectly. For example, if you clean fly ash with acetone beforehand, gives a higher strength than the untreated. Because when you are cleaning, that means there is no defect there. That means the bonding between the fly ash and the polymer is much more. It can work directly, okay? Because if you have defects, that means if there is dust and this and that, so that will intervene, all right? So these are similar things that people have to realize. The purity of polymer can influence the performance of the polymer, but okay, we have seen that. Although there is no direct correlation with mechanical properties, the impurities in fly ash such as unburnt carbon can give problems of texture and color of the composites. So this is something which knows that fly ash has unburnt carbon, and sometimes, now that carbon is not settling separately, that carbon is actually covering the fly ash, right? Because so that's what it can be sometimes good or sometimes may not be good. With the carbon, that carbon is not bonded to the fly ash. It's just covering the fly ash. It's like a coating on the fly ash. The particle size of the filler is known to affect the mechanical properties. Generally, smaller particles tend to have good contact with the polymer due to large surface area, and thereby gives better mechanical properties. Remember, let me ask you, when you have 100 micron particle size, and if you have the same amount of polymer, same quantity as 10 micron particle size, so what is the increased surface area in the 10 micron particle size? By how many times? How much? By how many? By what factor will the particle size is? No, the particle size is 10 times lower. So what is the surface area? By what factor is the surface area higher? How is area related to size? So r square. So 4 and pi, they are constant. So if r goes up by 10 times, then it comes. So if r comes down by 10 times, it's 100 times. So 100 times is a very important thing. Okay? Okay, sir. If you wish, you can continue your thing, and I can continue it later. No, that's all right. So if you can wait, that's fine. Okay. That's good, because that's fine. All right. I didn't want to. I thought you came in. All right. Now, smaller particle size also tend to agglomerate with each other and can lead to insufficient homogeneity. So that is another negative aspect of agglomerate particles. So agglomerate particles can act as crack initiator, and crack initiator means if you are applying stress, like Professor Kamalkar said, as the stress goes up. But if you have cracks there, that crack can induce the stress. So if you are saying that the stress is 10 MPa, the crack can increase. The local stress can go up to 30 MPa. So that will the tensile testing equipment will not realize, but the polymer material or that you are doing there, or the whatever, that will realize the thing, and it will affect the behavior of the property. Surface tension is something important. Normally surface tension, a lot of times, is a bit neglected. Okay, but surface tension is also a related feature which gives the matrix filler interaction. Rough filler surface appears to be weighted by polymers with difficulty, so that can lead to a decrease in strength. Small surface tension strengthens the matrix filler interaction, which can increase it. So it's good to have small surface tension material. Okay, let's go to the hardness. There is limited direct correlation in hardness in the composite properties, but the hardness of the filler should also be considered because it can affect the processing equipment. Now, processing means if you are using fly ash in the injection molding thing, injection molding, it melts the polymer, it comes through pipe and things like that. Now, the polymer has very low hardness, yes, but the fly ash particles, they have very high hardness, and when they are coming through this tube like that, pushing, so some of the fly ash can scratch the end of the inside aspects of the tube. Okay, so that can, after many things, that can become very ineffective, and it cannot work, or it can crack. So these things are worthwhile. So that effect is minimized by choosing small filler particles or adjusting the processing speed. Small filler particles means they will not have more sharp cracks. Okay, so that is this is something which people normally do not realize that, but this affects the equipment, and the hardness of this ceramics is so high, and it can scratch the thing. Okay, it can scratch the tubes when they're going through that. Okay, let's forget some of these things. Matrix filler interaction can be primary force, secondary force, hydrogen bond, and electrostatic interaction. So primary force, secondary force, they're all on a sudden you go to hydrogen bond, and then the electrostatic interaction, that it takes it to the electrical properties of the polymer. And there are two types of interactions, like matrix filler interaction and filler-filler interaction. So that is interesting, because normally people only think about matrix-filler interaction. But filler-filler interaction, remember in one of the cases we could show that there is a negative force of attraction, then there is a positive force of attraction. So within the fillers, they have different particles, different compositions, like in fly ash, so many different things. So some of the fillers can like each other, they have attraction, and some of the fillers, they don't like each other. So they like to kick each other away from that. And as they do that, it will generate small cracks. So it's worth knowing those things. All right? So that is what all this chapter of model, it is important. Filler-filler interaction causes aggregation and can lead to a decrease in the composite strength. So sometimes, like in some of the graphs which you showed, you could see that some of the composites, as you put more amount of composites, the strength comes down. And one likely thing is that the filler-filler interaction, which is involving generating a negative factor there, so that can answer your question. Remember you asked me the question, why is the strength going down? So depending on the filler content. So that is something which people normally do not realize, that they think filler and filler, because if you have one single filler, that's all right. Like if you're going to put silicon oxide or alumina, that's all right. But if you're going to put fly ash, which is a wide range of 8 to 10 fillers, so you have to know which filler has more, particularly the filler with high percentage, as long as they are not against each other, that's good. So you can select those compositions. The adhesive forces are mainly due to mechanical interlocking, electrostatic force, van der Waals force, liquid bridge and solid bridging, while repulsion force is mainly due to shear and elongation force during homogenizing. So these are the factors which have to be taken into account, or people take into account in the models. Now, one of the earlier models, Adams and Edmondson, described the adhesive force and the maximum hydrodynamic force acting as on spheres in a uniform shear field as a function of particle. So this equation 1 is on the left hand side, force of attraction, and this is on the right hand side, okay? Adhesion force and maximum adhesion, Fa, and hydrodynamic force. So these are given by this equation, one of the models. WAV is the reversible work of adhesion, D is the average particle size, and you have adhesive force, shear force. How does shear happen? Shear means, if you're pulling something like that, it's tensile. You're doing compressive. But shear happens all the time, because there is stress transfer even when you're doing tensile tests. So often the shear is happening along 45 degrees, and particularly if you have ductile material. The shear is always there. Only? So that component cannot be neglected. So therefore, the possibility of avoiding aggregation can be described by the ratio of the adhesion and shear force. So now you take a ratio of the adhesion and the other force, so then you come up with a new equation. So then what you can do, you could plot these graphs as a function of the particles. You can do that. From equation 3, it can be seen that aggregation can be minimized by increase in a shear rate and the particle size, or lowering the reversible work of adhesion. So this is how was the basement or basis of the thing. But increasing the shear rate can produce degradation of the polymer, while increase in particle size can lead to a decrease in strength. So you have to go for lesser particles, because that will be effective, and also you go for a lesser shear rate. The optimum condition can therefore be obtained by lowering the WAB through surface modification, and that's how it components. So eventually the properties of the composites are determined by components, composition, structure, and extent of interparticle interactions. So if you have different types of particles, you have one kind of interaction. If you have same type of particles but many particles, there is also some interaction, because particles have their own interactions. Right? If the polymer tries to separate them, the particles would try to go back to them. Okay, but in a way, sometimes it's interesting. But if the particles try to close to each other by compression, then compression gives better strength. Okay, because it prevents crack propagation, or it deletes crack propagation. So the theoretical models which normally give a general picture of the effects and can be expected for a particulate field polymer. Young's modulus, there are different models like Einstein theory, Hardness model, percolation theory, and rule of mixtures theory. So normally rule of mixture theory is used in composites, but here is a brief description of the Einstein theory. According to Einstein, the viscosity of a suspension of rigid spherical inclusions will have the following formula. So these are given here, like spherical inclusion, volume fraction, particulate interaction, particulate inclusions. Then Smallwood subsequently modified this equation, and thereby you can get an idea about the modulus of elasticity of the composites. And that can also be further modified by Guth et al., modified Einstein's equation. But Einstein's equation was the fundamental there. So this is how it goes like that. Mooney generated an equation, and Mooney's question was that Einstein's equation is applicable only for small concentration of fillers, when there is no interfiller particle interactions. What is no interfiller particle interaction? Remember, we showed you that when you have the particles, SEM, the SEM program can actually measure the distance, average distance between the particles. So in one of our latest work, we found that if you have more amount of fillers, okay, fly ash particle, then the distance between the particles can be about 15 to 20 micron. But if you have lesser amount, the distance between the particles can be about 60 microns or things like that. So if you have 60 microns, then there is lesser interaction between particles. The particles will interact only with the matrix. But if you have smaller distance, then particles will try to go back to themselves. So these are the effects which Mooney argued, and Mooney developed an equation which agreed with Einstein's equation for low volume fraction, and then taking into account the interparticle interaction at higher filler content. So Mooney modified this equation, and that's how it is given here. In this equation, K is the self-crowding factor. So that means it's defined as the volume occupied by the filler divided by the true filler volume. And this value is actually 1.35 to 1.95. That means what it says that you have the fillers, let's say the fillers have a volume of 1 unit, 1 cubic, whatever it is, cubic microns or things like that. But the fillers are there is some voids and something, they are occupying rooms there. Okay? So that is in about factor of 1.3 to factor of 2 high. So that is how the self-crowding factor, and the equation assumes that Poisson's ratio is 0.5. And that is normally the highest value of Poisson's ratio, except when you make a composite. If you are working in composite Poisson's ratio can be even greater than 1. Normally, in theory, Poisson's ratio should not be more than 0.33, but it can go up to higher in composites. But in some composites, you can have much higher than 0.33. So 0.33 for monolithic materials, but composites, it can go higher. So please keep that in mind. So these are other equations, some other equations given. Let me go through the results and measurement and combination of the, okay. This is a schematic diagram, the microscopic aspects of matrix interaction zones around spherical particles. So if you have one particle here, this is the diameter, and then the length is d plus delta d. This is the length. That means this is the height. And then if you have two particles, then that becomes distance between the particles. So this schematic of the matrix interaction around spherical particles, the particle is the shade, you have one particle, two particles. That's how the matrix interaction zones. So here this is matrix interaction zone, but if it comes closer, then there is more matrix interaction zone. And here, these fibers, the particles are coming closer, they are almost within the same matrix. So that makes a big difference. The situation changes at high filler concentration. The modulus is linear as a function of the V, where EC modulus of the composite is proportional to VE. So that means now the composite, if you have high filler particle concentrations, and that's, if you're going to use fly ash 40, 50, 60, 70, 80%, then you have to go for these equations. That's why this chapter is very important, because normally people, when talk about filler content or the equations, they assume that composite properties, it is true for all compositions. No. So if you're going to have higher concentration of filler, you have one type of effect, because interaction between the filler particles and the matrix. So that is where physics comes up. That is basically based on physics, okay? Physics of strength and things like that. So where in this equation, EC is the composite modulus, EB is the linear part of the composite modulus, V is the true volume fraction of the filler. What is the true volume fraction? Not the extra volume fraction, okay? True volume fraction. And VEP is the typical filler true volume fraction threshold. T is the elastic percolation exponent, and which is equal to about 3.8. So these are the way, and now that gives you this composite equation, including EB is the linear part of the composite equation, and EM is the matrix part of the composite equation. So this is how the models keep on improving it. Now, several extrinsic factors can influence the percolation threshold. According to Wu, the matrix thickness around filler particles is decreased as filler particle size decreases. So that is interesting, because if you have more filler, the distance between the filler matrix thickness will go down, because matrix, there will be not much of matrix, it will be more occupied the fillers, because the surface area is important, okay? And therefore the percolation threshold will be lower for matrix particles. The matrix thickness about the filler is increased with increasing side, okay? I'm trying to highlight the other parameters so that I put them in larger size. The other parameter in determining the percolation threshold is particle shape. Now, you have seen so far the fly ash particles which you have shown, they're almost all spherical. If it is spherical, that means it's uniform everywhere. But if they are not spherical, if they're rod-like and things, that means along the length you will have certain stress concentration, but as soon as you go to the end of the particles, there will be much more stress concentration or stress transfer. Okay? And that will put more force on the matrix. And sometimes the matrix can crack. That's why if you have longer things, you might ask the question, how about fiber reinforced plastics? So if you want to get stronger one, you have continuous fiber, like carbon fiber from one end to the other end. That will give you much less problem. That's why all composites in planes and other things, they have long carbon fibers, maybe meters after meter. But sometimes, if we have short carbon fibers, then you don't get that much of strength. All right? Rule of mixture, this is one which says typically this is what we had written, and this is what Babatosh came and wrote it on the, remember? So this is this special clear rule of mixture. And then this is modified rule of mixture. Another modified rule of mixture. Tensile strength, amount of force which the material applied without breaking it. So that is actually, that part is important, without breaking it. Tensile strength, all right? Now, that means you, once it breaks down, don't go to the breaking point, before the breaking point. Considering these phenomena, the equation for the tensile strength actually of polymer composites for a weak adhesion force is based on power law with the following general equation. So this is the type which many people do not use these kinds of equations. But this is where, this is the book chapter which Ahmad, I mentioned, Professor Kaur, what was the name, what is the name of the other co-editor of this book chapter, which you, she's from UK. What is the chapter? This is, it is, this Mohinder from Chawla was there also. This, she's a lady, she's from England. Yes, yes, yes. I think Leeds University, is it? University of Leeds? Yes. Yes. University of Leeds. Yes. So, all right, thank you. So the equation for tensile strength of polymer composite for a weak adhesion force is the power law with the following general version. So this is how, it is what knowing, particularly when you have things, and that can also be modified. So now, having gone through all these things, when you do your research, and often you get plenty of headaches as which model or what kind of things. So the best thing is having known all these things, but then you do your experiments or do your, and then evaluate your way, the standard way according to the standard, and you see which one, which model your material matches. And then you can go back to those mechanistic suggestions, and then you can say that, okay, that means our samples will have this kind of reaction or interaction, all right? So that will give you, that's why all these things are important, knowing this knowledge, because all those equations, they give you the mechanisms. And that's why Einstein's name is, we all know Einstein's name, okay? So things like that, and also all these modifications, so they will open up our eyes. We cannot go, our eyes cannot go inside the thing, but these models will open up our knowledge that this is perhaps what is happening, and you can improve it or you don't need to improve it. So quickly I'm going through some of this, and then once I show the tensile things, then I'll stop and we can continue later tomorrow, all right? Because the polypropylene was chosen as a base polymer for detailed studies, and the polypropylene was supplied by this company in Australia with diameter around a few micrometers to a few particles. So this is actually powder. You remember during the break, someone was asking me, and I said, how to make the things? I said, best is to have a powder. If you have a powder and if you have the material, all the filler also powder, then it is much easier to interact. Because if you're doing injection molding, they will mix much quickly. But if you do not have a powder, if you have larger size, larger spheres or cylindrical blocks, it is better to put them in a ball mill together with the powder and make sure that the polymers also become smaller particles. Okay, and also if you have, instead of large particle size, if you have small particle size, what advantage of that? Just now we asked, what thing becomes extra? Surface area becomes extra. So that the reactivity, and when it goes through the injection molding, is much easier. So these are some of the equations, and this is the polypropylene. Again, just a reminder of the photo, because we have gone through so many slides. So this is how the powder looks like. Toxicity, melting and crystallization temperature, crystallinity and melt flow index, they were determined. XRD pattern of polypropylene used indicates that there is high intensity sharp peaks. And by comparing the pattern with literature, it was concluded that polyethylene in this work has an isostatic configuration. So we have seen that. So this is the XRD of polypropylene used in this research. And this shows nice peaks. This is 2 theta nice sharp peaks. And that is a good start. Melting point, 165. Crystallization point, about 129 degrees C. Crystallinity is about 45%. That is the thermal property of polypropylene. The melt flow index was provided by the sample at 60 grams per 10 minutes. That the sample had a low viscosity. Now, typically, you can have 10 and above. So, if you have a higher melt flow index, then it's low viscosity. The fly ash used in this experiment was of Terang 63 from Cement Australia, Brisbane. Its composition is given in table 2. You have particles, silica, alumina, Fe2O3, TiO2. Some of the particles are a very small quantity, but that's what it shows. Like if you're making a composite using only silica in the particle, so there will be only interaction between the silica particles. But if you have other particles, then lots of interactions or disinteractions can happen. But that is something we cannot change. If you're going with fly ash, you have to accept whatever it is. So select fly ash which has better composition. Injection molded tensile space particulate samples of fly ash polypropylene composites were made at 210 degrees C. So the melting point was about 169, so you have about 40 to 45 degree more high temperature. And here, some of you had asked, what is the maximum fly ash content we can go for? And in these experiments, we had gone for, start as low as 2%, but as high as 80%. And PHR means this is parts per 100 of resin. This is when you're working in polymer, they don't talk about percentage, they say PHR. How much 100 resin and parts per 100 of resin. So the weight percent may be different from that, but this is actually parts per 100 of resin, PHR. So these are the fracture surfaces at 1000 magnification. This is normal, okay. ACM fracture surfaces. These are the different fly ash contents, and you can see that these are gold-coated samples. Now the tensile strength of the composites are given here. The strength versus particle size. This is top is 2%, and as you are going more into fly ash, and this is what it shows, the strength is coming down. That is with polypropylene that can happen. But this strength is not the only thing. Like we said that the impact fracture is more important also. All right. So an impact fracture we have seen goes up. But here we do this and we have to, and it has been analyzed as to which model these data match more. The slope, if you have volume fraction of calculation of Landon tensile strength. So this is another model. This is given like that. The data also reveals that there is good adhesion between the fly ash and the polypropylene. And then since thermal compressive stress and B value are not known in this Landon model, then these results from these two other models, Landon and Pugansky, could not be compared with the experimental value. So this is now what we are doing. Though going back to those tensile strength, these are three models which are there. Nielsen, Nicholas, and Landon. So this is the other three models, and this is actually our results. So it shows that whereas the other three models show that using this amount of participator particles, your tensile strength will go down, but we are happy to say that our material strength is much higher than what they predicted. So obviously all the bad things which are happening in those models, so in this fly ash model using up to 80 PHR, so that did not happen, and it's significantly higher even with 50 volume fraction of fly ash. All right, it still maintains. So that was a positive thing. And then Young's modulus is, as I've been saying, Young's modulus is the most important thing, because the Young's modulus is taken at very low displacement but in the linear region. So here you will see that if you use those equations, these equations, they would claim that all this, if you put volume fraction of the fabric, so up to 50%, someone says it will go down, someone says it will go up, and someone says it will go up there. And our thing is around the middle of that. Can you see that this dark one? This is the T63RT. That's what we have used. So we are happy that the modulus went up from about 2, just less than 2, to more than 5. So by how much factor did the modulus go up? 2 to about 250%, like it went up from 1.8 to 5.5. So 3 times 18 is 54, is that right? So that was, and that's when this paper was actually accepted in Fuel, which is a high impact factor thing, and they went through all this, and the strain at break, and that is normal. Ductility will go down because you have more fly ash, but still the the strain of break at start, that means for polypropylene it was about 8 or 9%, which is quite good. Remember one of the graphs where we had shown that compared with other things? But then when you use fly ash, you still have about close to 50%, you still have about between, this is Smith's model, this is Nielsen's model, but our results show that you still have about 3% strain there. So other models say that if you put this much of thing, your strain to failure will go down to about 1%, but our results show that no, our achievement, our fly ash composites using polypropylene had about 3 times more. So 3% is quite good and accepted. So at that point, I'll stop this lecture and we'll continue tomorrow. All right? I have my lectures tomorrow in the morning starting at 8:30. All right. So if you have time, if you have any questions, you can ask me, or but the other speaker is also waiting. Any questions? PHR is parts per 100 parts of resin. So if you have 100 grams of resin, and then you are putting 60 grams, 60 grams, so that is, so it's not as the percentage, it's parts per 100 resin. This is what the polymer industry do that. They said, we don't like the volume percent, weight percent. They said, it's funny. So if you are using 100 parts, tell us how much you will do. That means if you are using 1 kilo of resin, and if it's 60 parts, that means you use 600 grams of fly ash. Because it's sensible. The people who are working, they said, we don't have calculators. Can you speak loudly? Yes, but we'll get back to that. Yes, okay, to answer your question, by using fly ash, up to a certain amount, we obtained 50%, up to 50% improvement in sharpening impact property of polypropylene. So that will make you happy and makes us happy. Okay, and that is very unusual in other composites. And as I mentioned, the CP director, when he went there, and he said, how come with fly ash you are getting such improvement in impact factor? He said, strength and other things do not matter much, tensile strength, the impact, but that's how. And impact does not take any time. There is no stress transfer and no friendliness, so it's a overall just resistance to crack propagation. So that is what it is. We obtained up to 50% increase in the, and we'll get back to that later. All right? Does it answer your question?